Dear students, from now onwards, we will start Unit 4. Okay, so Unit 4 is the flow through pipes. Okay, flow through pipes. So last unit we seen flow through open channels, not just a VS like that. Okay, open channel. So in this unit, we will see the performance of the water or any fluid when it flowing through a pipe. Okay, or different types of pipes. So this is the syllabus for 4th unit. The first chapter is Reynolds Experiment, Reynolds number, loss of it through pipes, Darcy-Weisbach equation, minor losses. These are the first two chapters. Okay, Reynolds Experiment and major losses and minor losses. So next, total energy line, hydraulic grade line. These are the second chapters. And the third one, pipes in series. And the fourth one, equivalent pipes. Fifth one, pipes in parallel. Sixth one, siphon. And seventh one, branching of pipes. 3, reservoir problem. And eighth one, power transmission through pipes. And ninth one, analysis of pipe networks, Hardy-Cross method. And last one, 10th one, water hammer in pipes and control measures. So this is the content in Unit 4. So now we will start our first experiment. First chapter, Reynolds experiment. Okay. So before going to that Reynolds experiment, first we must know what is the Reynolds number. Okay. So the Reynolds number is an important dimensionless quantity. So there is no dimension for the Reynolds number. In fluid mechanics, used to help predict the flow patterns in different fluid flow situations. So we know that laminar flow and turbulent flow. Okay, so in laminar flow, the fluid particles are moving under well-defined path. Okay, so in case of turbulent flow, it is not moving under well-defined path; it is moving under a zigzag manner. So that is the turbulent flow. Okay, so this Reynolds number, it is a dimensionless number. This Reynolds number is very much useful for identifying the type of flow, whether it's laminar or transition or turbulent. Okay. So what is that Reynolds number? The Reynolds number is the ratio of inertial force. Okay, inertial force to the viscous force. So another name of viscous force is fluid friction force. So every fluid having some viscous force. Okay. So while fluid is traveling in a closed conduit, that means pipe. Example, pipe. So there will be a initial force is occurs. Okay, initial force. Okay, initial force means suppose force is applying in one side, the movement will be takes another side. Okay, suppose for example, we are traveling in a bus. Okay, the bus is moving at a speed of 50 kilometers per second, for example. So if the driver is suddenly applied the brake, what happened? So we will our body will move into the front side. Okay, that is called inertial force. Okay, so same manner occurs in the pipes also. Fluid moving in the pipes also. That is called inertial force. And viscous force. What is by viscous force? It is the fluid frictional force. Every fluid having some friction due to the wall of the pipe, and every fluid having some viscosity. So due to this, some viscous forces occurs. Okay. So the Reynolds number is nothing but it is the ratio of inertial force to the viscous force within a fluid which is subjected to relative internal movement due to different fluid velocities. Okay, that is the Reynolds number. So Reynolds is nothing but the name of the scientist who found the Reynolds number that we will discuss in next subsequent slides. So Reynolds was able to generalize his conclusion from his dye stream experiment, that is called a dye stream experiment, by the introduction of a dimensionless term RE. RE is nothing but Reynolds number. later called the Reynolds number, which was defined by Re is equal to B into D rho divided by mu. Okay, divided by mu. This rho divided by mu is nothing but a kinematic viscosity. Okay, inverse of kind. What is the formula for kinematic viscosity? Is nothing but dynamic viscosity divided by the density. Dynamic viscosity divided by the density. So here inverse is there. So here you can see rho is there and mu is there. Okay, see this term. Okay, so this term. So rho divided by mu. So it is the inverse of kinematic viscosity. So we can write this equation like this: V d divided by nu. Okay, this is called nu. So this is the Reynolds number formula, in which V is the mean velocity. V is the mean velocity. V is nothing but velocity of the fluid in the pipe. D is the diameter of the pipe. D is the diameter of the pipe. And rho, mu, and nu are the density, dynamic viscosity, and kinematic viscosity of the fluid flowing there in the pipe. So these two formulas are important formula while doing problems. Okay. Suppose in the problem they given only mu, means you have to use this formula. Okay, or they given only nu, means you have to use this formula. It is depends upon the problem what they ask in the question. Okay, so please be remember the formula. Re is equal to, that means Reynolds number equal to B d rho divided by mu, or other formula B d divided by mu. This is the other formula. Okay. So next we will go to the Reynolds experiment. In 1883, in the year of 1883, Osborne Reynolds is the scientist, demonstrated that there are two distinctly different types of flow by injecting a very thin stream of colored fluid having the same density of water into a large transparent tube through which is water is flowing. Okay, so in 1883, Osborne Reynolds gives some demonstration. In that demonstration, they taken one glass tube. The water is flowing in the glass tube. So in the glass tube, a dye color, okay, a color pigment is he injected. Okay, so in first, in very much less velocity in the fluid, that dye color is moving in a well-defined path. So after that, Reynolds increased the velocity of the fluid. Now what happened? The dye color is changes into move into zigzag manner. Okay. So that I will show in the next subsequent slide, that picture. So the apparatus required is a tank filled with water, a small reservoir filled with colored fluid or dye, a glass tube with bell mouth entrance, okay, a measuring tank, a regulating valve at the outlet of glass tube and at inlet of the dye injector, a stopwatch. So these are all the equipment apparatus required. And now you can see here, so this is the container filled with water. So this is the glass tube, transparent glass tube. This is the dye, that means color pigment is injected. This is a small hole is present here. A small hole is present here. Through this hole, the color dye, color pigment is injected in the glass tube. Okay. So you can see this line. So water, it shows the movement of the water, whether it is laminar or turbulent. This is the regulating valve. Okay. So this is a small experimental schematic diagram. When in the examination they ask to explain the Reynolds experiment, means you have to draw this diagram. Okay. So next, what is the procedure? Fill the tank with water. Fill the tank with water and leave it for some time, as the water in the tank should come to rest. Now fill the reservoir with a dye, generally potassium permanganate solution. What is the color of potassium permanganate solution? It is nothing but a pink color. Okay, I think you already used in chemistry lab, first year chemistry lab, potassium permanganate titration. Okay, so it is in pink color. Mostly it is used, which is nothing but colored fluid. The weight density of dye should be same as that of water. So both the density of water and the density of the color pigment should be same. Record the temperature of the water. Okay, using thermometer, record the temperature. Allow the flow through the glass tube at a very low rate. That means very low velocity initially by partially opening the outlet valve of a glass tube. Okay. So when the flow is stable, open the inlet valve of dye injector and allow the colored fluid to flow through the glass tube. Okay. So now what happened? Let us see. Observe the appearance of the dye filament. Okay. Dye filament. That filament is visible in a clear manner. Dye filament in the glass tube and note on the type of flow obtained for that particular discharge. Okay. Take a stopwatch and note down the volume of water collected in measuring for certain interval of time. Repeat the above procedure for different discharge rates. So initially very low discharge, very low velocity. So now second trial you slightly increase the discharge or slightly increase the velocity. So now again note down the pattern and note down the volume. Okay. So finally, calculate the Reynolds number for each type of flow using that formula. Okay. So this is the Reynolds Osborne in 1983 demonstrating the onset of turbulent flow. Okay. So this apparatus is still at the University of Manchester. So in 1983, Reynolds physically demonstrate the experiment in front of all the scientists. Okay, so still that instrument is available in the University of Manchester. Okay, so you want to see that instrument, you can see this one. So this is the instrument he used to demonstrate the Reynolds number. Okay, so you can see here, this is the dye solution which is injected in this small diameter glass tube. Okay, so still is there for the memories of the Reynolds Osborne Reynolds, they maintaining this instrument. Okay, from this instrument only he deliver the lecture, demonstrate the lecture and find out the Reynolds number. Okay, so you can see here initially the experiment showed the flow state demonstrated by Reynolds. Okay, this is the lab experiment. You can see here this is a dye filament. This is a glass tube. So initially you can see here the very low velocity. This green color is here moving under well-defined bond. You can see the very green color. So the Reynolds number for this is less than 2000. That means flow classification is lambda flow. If the Reynolds number is less than 2000 means the flow classification is lambda flow. Now, just to increase the velocity of flow, what happened? You can see here this green color somewhat moving in the zigzag manner. So here the Reynolds number is 2000 to 4000. So the flow classification is transitional. So next, again increase the velocity. You can see the difference. Here a slight movement, but here more movement. So here transitional into turbulent. And here you can see, we can't see that green color because the velocity discharge is more. So it is greater than 4000. The Reynolds number is greater than 4000 and it is called a turbulent flow. It is called turbulent flow. Okay. So these are all the Reynolds experiment. So while in examination, you have to draw the schematic diagram of the experiment and also we have to show this type of figure, this type of 4 figures. So laminar flow, transitional, and transitional to turbulent and turbulent. And note on the corresponding Reynolds number less than for 2000, 2000 to 4000, and greater than 4000. So this is very important one. Students, now we will see the Reynolds experiment animation and videos. Okay, so for better understand, because this is important 10-mark question in fluid mechanics 4th unit, first chapter. Okay, so now we will see the animation video first.
So before going to this experiment, let us know the definition of Reynolds number. So Reynolds number is a non-dimensional parameter which helps us to identify the type of flow. So generally the Reynolds number is given by inertia force to viscous force. So based on the Reynolds number, so the fluid flow is characterized into laminar flow, turbulent flow and transitional flow. So to understand these flow, the Reynolds experiment was conducted by Reynolds in 1983. So this experiment gives a clear picture about how laminar and turbulent and transitional flow takes place in the fluid flow. The experimental setup consists of water tank, a dye tank and glass tube and regulating valve. In this
So here you can see this is the water tank, and this red color is the dye tank. This is the color pigment stored in this dye tank, and this is the transparent pipe, transparent glass tube pipe, and this is the control valve. From using this valve only, we are adjusting the discharge. Okay, suppose we want to low discharge, low velocity means we have to open slightly. So otherwise, we want to more discharge means we have to open more. Okay.
experiment, the water from the water tank is allowed to flow through the glass tube. The flow velocity of is varied by operating a regulating valve. At the same time, the liquid dye having the same specific weight as that of water is introduced into the glass tube. And during this operation, the following results are observed. At lower velocity of in a flow, the filament in the glass tube is in the form of in a straight line. So this straight line of filament dye is parallel to the glass tube, which indicates that flow is laminar. When the velocity of a flow is increased to some higher values, the filament dye is nowhere a straight line and it takes some wavy nature, which indicates that the flow is not laminar. When the flow velocity of a fluid is increased to a higher value, the complete wave of a dye disappears and it diffused into the water. It means that the fluid particles of a dye are moving in a random fashion, which shows the case of turbulent flow. In this case, the mixing of dye filament and water is intense and flow is irregular, random and disorder. So in a general case, if the Reynolds number is less than 2000, then the flow is known as laminar flow. If the Reynolds number is more than 4000, then the flow is called turbulent flow. If the Reynolds number lies between 2000 and 4000, then the flow is transitional flow.
Students, next you can see the next video. This video represents the three different flows. Okay, so now you can see the filament is moving in a straight line. It is laminar flow. That means Reynolds number less than 2000. Now it is changed into from laminar to transition. So it is in between 2000 to 4000. Again, you are increasing the rate of flow. That means discharge means the transition flow is converted into what is that? Turbulent flow. Okay. So under this case, the Reynolds number is greater than 4000. Okay. Okay, students. Next, we will see the how to do the experiment in the laboratory for better understand. for your better understand. So we will discuss how to do this experiment in laboratory. Okay. So for this, we need a bucket of water and dye pigment, uh, colored solution, and one injection and a transparent tube. Okay, everything needed. So let us start the experiment. Please watch carefully the pattern of the flow of the dye. Here a blue color dye is used. Okay, so we can observe the laminar transition and turbulent very clearly. So please this body watch the video carefully.
Hello guys, my name is Rohit. In this video, we will be learning about laminar and turbulent flow through an experiment. For this experiment, we need a water tank, a dye tank, a flex pipe and a tap. We have used a flex pipe of length 1.5 meter and dia ½ inch and a needle to insert a low viscous ink into the water flow. Now let us start with the experiment by finding the discharge. We are using a container with a graduation scale. We will find the time taken to fill 200 ml. For laminar flow, the discharge rate should be low. So let us slightly open the tap so that the rate of flow is less. Since it takes a long time to fill the container, let us fast forward the video. It has taken 1 minute 53 seconds. For this flow rate, let us check the type of flow. As we see, this is a laminar flow.
You can see the laminar flow. So the filament, the blue color filament is moving along a straight line. You can see. So now the discharge is very, very low. So it's moving in a straight line in the liquid.
Now let us open the tap completely so that we get a higher discharge.
So for more discharge, we have to open fully. Now you can see observe the dye filament moving.
It has taken 5 seconds to fill 200 ml. From this flow rate, let us find the type of flow. As we see, we get a turbulent flow.
So it is not a straight line.
Theoretically,
it is a turbulent flow.
Volume over time equal to discharge. To find the value of discharge, we use the value of discharge to calculate velocity using the relation discharge is equal to product of area of cross section of the flex tube and velocity of water. The velocity is in turn used to find the Reynolds number. For the lower discharge as shown in the first part of the video, we get the Reynolds number as 199, which is less than 2000. Hence the flow is laminar. For the higher discharge, we get the Reynolds number as 4500, which is more than 4000. Hence the flow is turbulent. Thank you.
So based on this, we can say whether it is turbulent flow or laminar flow based on the Reynolds number. So these are all the simple experiment we can do in our laboratory. Okay. So I hope all of you understand the concept of laminar flow and turbulent flow. Okay, students. So next, losses through the pipes. There are different losses is there. What is meant by losses? Suppose in one place, at starting place, your water is discharged 5 meter cube per second. Okay, but in another side, we didn't get 5 meter cube per second. We get only 4.8 meter cube per second. Okay, so what happened that balance 0.2 meter cube per second? That is the losses. Okay, so losses may occur in many cases. Okay, so there are two major type of losses is there, major losses and minor losses. So major losses occurs mainly due to the friction in the pipe. Okay, friction in the wall of the pipe. And minor losses occurs due to sudden enlargement of the pipe, sudden contraction of the pipe bend, and different valves, tees, bends, reduces. Okay, so these are the causes of the losses. Okay, so here you can, in this picture you can see major energy losses due to friction, and minor energy losses sudden expansion, sudden contraction, a bend in pipe fitting, and obstruction in your pipe. So whenever in the, suppose unfortunately a stone is there in that a large diameter pipe, say over 300 mm diameter pipe, in between a stone is there. That is called one obstruction. Okay, for example, I am telling. Okay, so in that also that discharge will be affect and velocity will affect. Okay, that is called energy losses. So when your fluid is, first we will see the major losses. After that we will discuss minor losses. When your fluid is flowing through a pipe, the fluid experience some resistance due to which some of the energy of the fluid is lost. Okay, that is the major losses. So for finding the major losses, one of the equation is used, that is called the Darcy friction factor formula. So using the friction factor formula, we can easily find the how much head loss is occurs due to friction. So HF is equal to 4FLB squared divided by 2GD. This is the formula. Okay. So the Darcy equation is a theoretical equation that predicts the frictional energy loss in a pipe based on the velocity of the fluid and the resistance due to friction. It is used almost exclusively to calculate head loss due to friction. See, loss due to friction is the major loss in a pipe. So compared to, there are minor, for that only it is called major loss due to friction. Okay. So there will be a derivation is there, how to get this HF is equal to 4FLB squared divided by 2GD. That is called Darcy-Weisbach equation is there. So that equation we will discuss in the next class. Okay, students. So thank you for your understand. I hope all of you understand the Reynolds experiment is very, very important 10 more question, theoretical question. Okay. So all of you understand, I hope all of you understand the Reynolds experiment, Reynolds number, and laminar flow, turbulent flow, and the different types of losses. So major losses and minor losses. So from next class onwards, we will discuss in deep about major losses. Okay, next class is major losses, and again we will discuss minor losses. Okay, students. So thank you for the understanding.